We'll just give a few more seconds for people to enter the webinar. We can see you all filing in now. But just to say welcome to you all to this Energy Technology Perspectives webinar. The topic for today is near zero emissions material manufacturing and trade. My name is Peter, and I'm an analyst here in the Energy Technology Policy Division of the IEA, and I'm joined by my colleagues Alexandre, Richard, and Leo. We're going to be talking today about this topic of materials and near zero emissions materials specifically, and this is the fourth and final webinar in a deep dive series that we've been putting out following the launch of the Energy Technology Perspectives 2024 edition on the 30th of October. It follows previous deep dives this week and last week on the topic of clean technologies, on shipping and emerging market opportunities, and all of these webinars, including this one, will be available on the IEA's YouTube channel in due course. I'm just going to share my screen. So these are the previous webinars that I mentioned. Our topic for today, near zero emissions materials production and trade. The presentation today will be structured in three parts. My colleague Alexandre is going to set the scene using market sizes, investments, and emissions, among other analytical quantities, to put this topic in the context of the broader Energy Technology Perspectives 2024 analysis scope and findings. My colleague Richard will then take up the topics of the deep dive areas of the deep dive regional focuses in our report, looking in particular at the US, at the EU, at China, and India. And then my colleague Leo will take us through the findings on some of the opportunities that we've identified for emerging economies, particularly in Latin America and in Africa. We're also very fortunate today to be joined by representatives from the global steel and aluminium industries. I will introduce them properly after the main presentation, at which point they'll provide reflections on the content that we've presented here today. Please don't hesitate throughout the presentation to use the Q&A functionality in the Zoom. You can drop questions in the chat anytime, and any questions that we don't get round to answering, we'll be able to follow up with you after the webinar by email. So without further ado, I'd like to hand it over to my colleague Alexandre to get us going on the first item in the material.
Thanks, Peter. So I'll start talking about the markets we have studied for this report. So today, the market for clean technologies, which includes EVs, the batteries, solar PV, wind turbines, heat pumps, and electrolyzers, is less than half the size of the market for the three materials we focused on, so steel, aluminium, and ammonia. This is quite a new situation because just in 2010, the market for clean technologies was only around $100 billion. But it grew a lot since then, and especially since 2020, with driven by the rapid deployment of electric vehicles. But over the same period, the market for material has been more or less stable. And by 2035, the clean technology market could almost triple in size and overtake the market for materials, and even more impressive, become on par with the crude oil market we have seen in recent years. So just for context, our stated policy scenarios, or STEPs, is designed to show a picture of where the energy system might head under the current policy landscape, but does not assume aspirational climate targets are achieved. On the other hand, our APS, or announced policy scenarios, assumes governments meet their climate commitments in full and on time. And in this scenario, the clean technology market is 25% greater than in STEPs. But it is with near zero emission material, the hashed areas you see here, that the difference between the scenarios is the most pronounced. The market is almost 150% larger than in STEPs and grows more than 50 times compared to today. And so for context again, we refer to technologies that can produce either steel from iron, aluminium from bauxite, or ammonia, with emission intensities that are compatible with the IEA's net zero emission by 2050 scenario as near zero emission technologies. And this could include, for instance, hydrogen-based direct reduced iron or CCUS-equipped steam methane reforming, just to name a few. And to feed these markets, a lot of investments are needed. And between 2022 and 2023, investment for clean technologies manufacturing grew by 50% to reach almost 250 billion US dollars per year. And if this level of yearly investment is maintained, it will be more than enough to meet the average needs of the coming decade, be it in our steps or APS scenarios. Indeed, for certain production steps like PV module assembly, installed manufacturing capacity today is already sufficient to meet demand in 2035, thus lowering the need for investment in the future. But for near zero emission material production, even if investment has been growing over recent years, a massive ramp up is still needed to achieve the emission reduction ambition in the announced pledge scenario. So clean technology manufacturing also has an effect on the demand for materials. So wind turbines need steel, solar PV modules need aluminum, and EVs need both. But in total, manufacturing clean technologies represent about 1% of steel demand and 4% of aluminum today. And those values are expected to grow by 2035. And for aluminum in particular, they have a noticeable impact on demand. And to note, this doesn't include the additional demand from installing those technologies and from energy infrastructures, such as all the aluminum cables used for expanding the electricity grid. For ammonia, there's a different story. Today, most of it is used for fertilizer application, and this demand will remain strong as the world population continues to grow and countries work on guaranteeing food security. But a new form of ammonia use is emerging, and it's used as an energy carrier, mainly in the shipping industry or the power sector. And talking about the shipping, this is not a sector to overlook, as it supports 80% of global trade by mass and contributes 2% of global energy-related emissions. And ammonia looks to be a promising vector for decarbonizing this international shipping. And indeed, in the APS, those energy applications represent 85% of the increase in ammonia demand, with shipping playing the biggest part. Thus, ammonia is a key contributor to the 60% decline in emission from the shipping sector by 2035 in this scenario. Outside of those end-use considerations, other factors are impacting material demand. And the two major trends I have to mention is that on one hand, the Chinese construction sector is slowing down, reducing its demand for steel. And on the other hand, demand is increasing from other emerging markets. And as a result of all those factors combined, demand for ammonia increased by 70% by 2035 in the APS. Aluminum grows by 25% and steel by a little less than 10%. So the production of materials, as you all know, is very emission intensive. Today, 3.5 gigaton of CO2 are emitted directly from those industries, with steel alone representing 7% of global energy-related emissions, plus 2% if you combine aluminum and ammonia. For comparison, the direct emissions from manufacturing all those clean technologies we discussed before and their components are today 100 times smaller than those of materials. And despite the increase in material demand we just saw, in the emissions still managed to drop by 2% in the STEP scenario by 2035. And this is mainly thanks to a higher share of scrap use, reducing the need for primary production of steel and aluminum, which is particularly emission intensive. And in the APS, things go even further to meet climate goals, with a 20% emission reduction compared to today. Here, scrap, material efficiency, and energy efficiency play an important role. But emissions for primary production also needs to decrease. And to achieve this, we need near zero emission production technologies. And in 2035, about 15% of primary steel and 40% of ammonia come from such routes. The deployment of these clean technologies, of course, didn't come out of nowhere. The first wind turbines were used to generate electricity already in the end of the 19th century, and the first solar cells were created in 1953. So those technologies had gradually developed, and today they have reached a level of maturity sufficient to compete with incumbent technologies and attract a lot of investments. But the production of near zero emissions material is more recent. Inert anode technology for aluminum production was demonstrated in 2009, And the first direct reduced iron plants with 100% electrolytic hydrogen started construction just a few years ago. Ammonia is maybe the exception, with production relying on hydropower already existing a century ago, but the use of variable renewable electricity for large-scale production is a challenge that has been tackled only in recent years. So while these technologies are at an earlier stage in their development compared to solar, wind, or batteries, they're still crucial to achieve our climate goals. So we need to keep progressing on development and demonstration to make the large-scale adoption feasible in the coming years. And another potential challenge associated with near-zero emission technologies is their costs, because on average, the levelized cost of their production is higher than conventional technologies. This is mainly linked to a greater initial investment, and often a lot of them require a shift to other fuels like electricity, which often can be more expensive than traditional use of fossil fuels. However, in certain cases, as you can see in this figure, when renewable energy is affordable and with the right policy support, such as carbon pricing, near-zero emission solution can become more cost-effective than conventional ones. In addition, continued investment in near-zero emission material production helps to bring down the cost in the long run through innovation and learning by doing. And I'll pass on to Richard to present some key regional results.
Thanks very much, Alexander. So, firstly, manufacturing capacity and production of these materials is somewhat concentrated in key regions, most notably China. However, this isn't unexpected. Global demand is dominated by these regions' domestic demand. And unlike clean technology manufacturing, where for elements of the solar PV or battery supply chain, the top 3 countries supply 95% of global production, the materials production market is large, developed, and it's distributed across many more countries and regions. However, currently the pipeline of near-zero emissions production of these materials is more concentrated. This is to be expected, given the early stage nature of some of these technologies. For example, aluminium, there is only one demonstration project of scale, the ELYSIS project in Canada. And so by definition, the project pipeline will be concentrated in one country. However, to ensure a sustainable and rapid energy transition worldwide, learnings from these first projects need to be shared internationally, particularly with emerging markets. This could be through government collaboration or learnings within multinational companies. Regional dynamics for production and trade of these materials will also shift in a scenario where government climate pledges are met in full and on time. Driven by rising new energy applications we mentioned earlier, this is the green bar here. Near-zero emissions ammonia production could become a significant contributor to total ammonia production, more than offsetting increases in demand. For aluminium, near-zero emissions primary production technologies are further away from commercialization. And so by 2035, they're only beginning to penetrate the market under the same scenario. However, secondary production with scrap as an input can play an increasing role. See the dark blue bar here. Growing amounts of the aluminium products, which were sort of put in place 15 or 20 years ago, are starting to come to the end of their life cycle and be available for recycling. And this will reduce the need for new primary production and allow us to supply the rising demands from solar PV or new aluminium cables. Steel production dynamics can be quite complex, and we work a lot on this in collaboration with World Steel, the wider industry. For example, our steel technology roadmap, and our work through the Climate Club on standards and definitions for near-zero emission steel. Rising amounts of scrap will be used in the future in steel. The line for steel can be a bit blurry, as many furnaces use a mixture of scrap and primary iron as their input. Production in India, particularly, is likely to rise significantly with its ongoing development, and production in China could decrease slightly in line with sort of decreasing demand from real estate and infrastructure build-out. By 2035, near-zero emissions production could become a significant but not a dominant player in the market. And this helps countries meet their climate pledges, and for this, advanced economies are expected to transition slightly more quickly. For trade, though uncertain, the picture could remain more static. Given China's decreasing steel demand and relatively young capacity for production, it is likely some steel export could remain, despite the sort of pivot that the government is taking forward towards new productive forces and somewhat away from the energy-intensive industries. China's exports in 2023 and 2024 were higher than the recent years, and a slight decrease might occur in the future, given the crunch felt by other countries' steel producers, the trade tensions this has caused, and the policy responses to counteract this, which are being imposed, like anti-dumping duties. China is also likely to remain self-sufficient in scrap, given its policies and the large scrap resource in those products which are beginning to come to an end of life in China. The EU and US trade picture could remain somewhat stable, with marginal increased scrap exports and steel net imports. But India is an interesting one. As we saw on the last slide, its steel demand and production is rising fast in line with its economic development. It currently imports some scrap, which helps to boost its production. And this import could expand somewhat, allowing India to continue to grow its steel production while moving slightly away from emissions-intensive production of iron. Each region comes into the energy transition in a different context. So one element of this is the manufacturing capacity in each region. Advanced economies generally have older steel-making capacity to the right of this graph. And much of this is a pivot point for reinvestment. Do they invest in blast furnace capacity, in direct reduced iron, or switch to a production model based on higher scrap content? Emerging market and developing economies such as India and China generally have younger capacity, and the considerations are different. How can they make their climate pledges while continuing to develop? Do they continue to build, refit, and replenish this capacity? And might this require some retrofitting with carbon capture later on in the energy transition? Similarly, production cost provides probably the key metric for investment decisions. There are others, such as customer location, but production cost is key. For the cost of producing materials using low emissions hydrogen, which can be part of the near zero emissions materials makeup, different regions have different contexts, mostly driven by the energy, labor, and capital costs. While there is significant variation between different member states in the European Union, the cost of near zero emissions materials production there can be significantly above other major regions. This suggests the European Union could benefit from forming strategic partnerships, allowing it to focus on specific elements of material supply chains and remain competitive. This is why we investigated the costs of fulfilling steel demand in the European Union, comparing the cost of domestic production to different strategic partnerships with Brazil. For this, we considered a context similar to the EU's Carbon Border Adjustment Mechanism, or CBAM, though the exact details of how this policy will be implemented are still slightly unclear. Firstly, the context for conventional production. Both imported steel from Brazil and domestic steel see similar carbon costs because of the impact of CBAM. Domestic production is slightly more expensive than imported steel, though it remains well within the range of uncertainty. Now, the same context for near zero emissions production. Immediately, we can see here that energy costs, such as for producing hydrogen, the light green bar here, are much higher in the EU. And compared to conventional production, the gap grows between domestic steel and steel produced in Brazil. This is to be expected. Brazil is a country with abundant, low-cost renewable resources. However, CBAM also addresses its mandate. Imports of near zero emission steel are cheaper in this case than conventional imports because of the CBAM costs applied to those conventional imports. Now, for the EU, switching to near zero emission steel and therefore having a larger competitiveness gap might not be the ideal outcome of CBAM or the energy transition as a whole. So, how to preserve some steel making and associated security and economic benefits in Europe? One option could be to import energy resources such as hydrogen from Brazil. While there is some scope for bringing down hydrogen transport costs with innovation, it's uncertain whether this will be a cost-competitive option. However, splitting the steel supply chain at a different point could bring benefits. What if you did the iron making step, the most energy-intensive part of that steel making, in Brazil, where both the iron ore and renewable resources are slightly concentrated, and you did the steel making step in the EU, which combines an important demand and a large pool of technical know-how. Initial estimates suggest that this could be cost competitive with imported steel on a pure cost of production basis. However, this could be the most attractive option, enabling countries or regions such as Brazil and the EU to focus their efforts where their comparative advantage might lie. This is just one example of potential opportunities which might be brought about by the energy transition and how strategic partnerships could enable both parties to benefit. Now I'll pass over to my colleague Leonardo to take you through some further opportunities in emerging markets.
Thank you, Richard. So first, let's have a look at how investment decisions in supply chains are taken. They are largely driven by cost-related factors, but there are also other underlying factors that have an important influence. For example, the ease of doing business in a country has an outsized impact on inward foreign direct investment in emerging markets in particular. Attracting capital to develop new manufacturing infrastructure requires a positive business environment, which depends on the presence of clear laws, streamlined taxation processes, but also banking and the financial system. Access to transport infrastructure is another important factor, especially in the case of bulk materials that are destined for export. Having existing, well-connected and efficient transport infrastructure can give countries a leg up when developing new infrastructure in hubs by reducing the need for additional investment and reducing the lead times. The presence of a skilled workforce can also play a key role in the decision-making to establish a new manufacturing facility in a country. Having experienced people that can take new jobs and be operative in minimum training needs can avoid delays in the production ramp-up and minimize risks of underperformance that can bring projects to a failure. For the analysis performed in ETP24, we have identified then 12 enabling factors measured by over 60 individual indicators, which we split in three main categories, namely the business environment indeed, energy and transport infrastructure, and resource and domestic markets. In today's material supply chains, emerging markets are generally big exporters of raw materials, and we have assessed here the opportunity for them to move up the supply chain, unlocking the potential that near zero emissions production in particular could offer to these countries. Today's steel supply chains for materials rely heavily on global trade. Looking at, for instance, at the iron and steel supply chain, we have trade in iron ore that accounts for about 10% of global trade by mass, equivalent to 1.6 billion tons. Today, Australia and Brazil are by far the largest exporters of iron ore, followed by South Africa. And the one single route from Australia to China makes up to nearly 50% of global trade in iron ore, meaning 5% of global trade in master. By contrast, there is currently much less trade in iron, just over 1% of the mass of iron ore. This is exported mainly from Russia, Brazil, and Oman. Interestingly, while direct reduced iron represent only 1/10 of iron production, almost half of the iron traded is in this form. This limited trade in iron is because most of the steelmaking facilities involve the production of iron and steel in just one integrated step, meaning that there is less opportunity to trade the intermediate product, iron. Indeed, semi-finished and finished steel products, including flat, long, and tubular products, are much more traded. 435 megatons of steel were exported in 2023 in this form. China hit a record high exporting about 95 megatons of steel products. EU countries are also large exporters, leveraging on their common market, which was established in the last century with steel as one of the first pillars. And Japan and Korea are also large exporters of steel products. And given the large variety of quality and products, the steel market sees many actors trading with each other. All the biggest exporters register also some imports. This is an important difference compared to the iron ore market, for instance, where trade is usually unidirectional from resource-rich countries to the consumers. Fairly significant quantities of steel scrap are also exported. This mostly comes from the advanced economies, such as the US, EU, and the UK, whose economies contain a large stock of steel-containing products currently being used. When traded, the scrap is then generally processed and sorted in emerging markets and then recycled to produce new steel products. Now, let's delve into the opportunities for the African continent, in particular in the iron and steel sector. Africa as a continent is currently a net exporter of 72 megatons of iron ore, with South Africa being the third largest exporter globally, and West African countries having large and still untapped iron ore reserves. Furthermore, the region is rich in other metals, such as chromium, used in many steel alloys. We investigated how African countries could leverage their good energy and material resources to build up their clean industries and potentially even export to regions with less favorable cost fundamentals. For instance, in our high potential case, where we explore further opportunities for emerging markets, we see the African continent together that exports 15 megatons of hot briquette iron by 2050, mostly to Europe and Japan. Because of the further processing which takes place, this iron could be worth more than 4 times the same amount of iron ore. This has also knock-on impacts, because the presence of iron making also helps African domestic steel industry develop, boosting domestic steel production and enabling Africa to supply its own market with domestically produced steel, reducing its import dependence and even becoming a net exporter by 2050. As mentioned before in the EU-Brazil example by Richard, with the right strategic partnerships, this could be a win-win situation for emerging markets and advanced economies, and could foster emission reductions in the steel sector. Similarly, then, we looked at the opportunities for emerging markets in Latin America to take advantage of the energy transition. Despite being a considerable user of nitrogen fertilizers, the region produces very little ammonia, particularly compared to other emerging markets, and mostly imports the fertilizers which it uses. Trinidad and Tobago is the most relevant ammonia producer in the region, which then exports most of its production to the US, with further processing into fertilizers indeed taking place elsewhere. But thanks to its abundant potential for affordable clean energy, the region could increase its ammonia production through near zero emissions processes. And again, in the high potential case, this could allow the region to supply existing domestic applications like growing fertilizers demand, but it can also supply growth for new energy applications domestically, such as shipping. And once domestic demands are fulfilled, supply a fast expanding export market. Of these export markets, some demand remains for existing application in fertilizers and other chemicals, but the majority of it is for new energy applications. This development could, for instance, allow Brazil to meet its target of halving fertilizers import by 2040. And this draw to a close. I'll pass back to Peter again. Thank you.
Thanks very much, Leo and Alexandre and Richard, for those fantastic insights. I'm just going to stop sharing my screen here to make everything bigger. I'd like now to turn to Andrew Purvis, if he's able to perfect. Andrew, he's Director of Sustainable Manufacturing at the World Steel Association, a body that, as I'm sure our listeners will know, represents the interests of the global steel industry. And we'd like to hear from Andy as to any reflections that he's had on things that he's just seen, or the ETP report more broadly, as they pertain to the steel industry. Andy, over to you.
Thank you, Peter. Hopefully you can hear me okay.
Yeah, great.
Excellent. Look, thanks for having me on. I think the report, as always, presents an interesting, I think, a useful assessment of what we know about material use now and how that's going to shift in the coming decades as we globally transition. I think it's clear that steel as a material will enable this broader societal transformation. All the low carbon solutions that we can talk about are steel intensive, but it's also clear in my mind that what our industry needs to do over the coming decades. I think to begin with, it's going to be about efficiency. We understand what we need to do. We need to make sure every ton of steel that we make is made as efficiently as possible. Through our step-up program, we understand the key levers, raw materials, energy efficiency, yield, and process reliability. These are things that can be done now. You touched on scrap as well. I mean, scrap is going to play a really important role. As you touched on, generation is going to increase, particularly in China, but the availability of scrap is a function of past production and the lifetime of the steel product. So perhaps circular approaches can help improve recovery, but there isn't going to be enough scrap. We're probably going to need 1 billion tons or so of virgin material by 2050. So scrap will play a fantastic role in reducing emissions, but we need to go further. And I think that's the last step, if you like, the breakthrough technology, and that we need to change the way we make steel, and specifically the way we make iron. And that transition is likely to take a long time, but we're starting to see first movers now really demonstrating these technologies, whether they're hydrogen-based, carbon capture and storage, or less mature technologies. I think we need a decade of action, and the next 10 years are going to be critical in terms of proving, really proving these technologies at a commercial scale and to build confidence. I think there's clearly also a number of questions which occur to me. One is, how far will material efficiency take us? You talked about that as a key tool, and it is. Steel will make this transition possible, but it's not clear to me at this stage how much of this increased demand will be reduced by material efficiency and other circular approaches. I think there's different scenarios, there's different views, and clearly if society demands more steel, it's going to be a bigger challenge from an emissions reduction perspective. You talked also about the production and trade of low emissions iron and how this will affect the industry. Again, I think this is a really big question. As long as I've been in the industry, people have been asking, why are we shipping rocks around the world? And it looks like that question's really being addressed now. This is a potential new industry, this dislocation of iron making and steel making. It would be a big change to the structure of the industry and supply chains, with potential changes of risk. And as you touched on, new regions like Africa potentially playing a much more significant role in the iron and steel industry. Free and fair trade is another question. Can free and fair trade reduce investment in additional capacity? Arguably, it's a difficult time for trade, but the reality is we're an industry with a significant overcapacity problem, and free and fair trade is certainly one tool that could help to reduce that, whether it's trade in steel products or materials that feed into making steel. And finally, infrastructure and energy. I think in the past, if you were going to build a steel plant, you didn't need to worry about where you're going to get your energy from. You just build a deep water port and import coal. There's no question of where you get your ore from. But now I think those other enabling factors are becoming more important, specifically energy, which the report touched on. For example, if you're going to shift to hydrogen, you do need to be confident that you're going to have low carbon energy or hydrogen available to you in the volumes that you need and at a competitive price. I think that's also true of carbon dioxide, transportation and storage infrastructure. So in summary, look, I think it's a great report. It's asked a lot of really interesting questions, but there's still a lot of, some of which we don't quite have the answers yet, but it's an interesting time ahead.
Absolutely, Andy. Well, thank you very much for those insights. Very thought-provoking as always. I'd now like to turn to our colleague Marlin Bertram, who's joined us from the International Aluminium Institute. She's the Director of Scenarios and Forecasts. And Marlin, in the same spirit, will provide us with some reflections on behalf of the aluminium industry. Over to you, Marlin.
Thank you very much for having me here. First of all, we really appreciate the work you're doing on aluminium. As you know, we are heavily relying on your scenarios to develop our decarbonization strategies. So thank you very much for all that work. Of course, aluminium is a bit of a different sector because 60% of our emissions come from electricity. And obviously, most of the plans or companies that are looking at decarbonization, especially the ones having to rely on fossil fuel for their electricity, will, of course, focus on that part first, and then look at the part that you are focusing on, the direct emissions and the emissions from thermal energy. So for me, of course, was no surprise to see no or near zero emission production in 2022 and 2023 for the aluminium sector. Of course, that's unfortunate, but yes, this, and I think Richard mentioned that, obviously the reason for that is we don't have a solution yet, or it's in development to look at the direct CO2 emissions and also on our PFC emissions coming from the smelters. Saying that, of course, we do see near zero emission production in alumina, actually, which is great to see. So there is already a big move there where we see very, very low ones. And what we think is once the technologies become available, we will see a step change in the aluminium sector rather than a slow decline of emissions. But these, as I said, the technologies are not there yet. What is always puzzling me, and thank you for putting that into your report, is the investments in near zero emissions. And again, it's nothing in aluminium sector, which is very unfortunate, especially if you look at, again, that was part of your slide, at the increase in demand and for aluminium, and also increase in clean technologies that need more and more aluminium. So for me, this is a bit of a mismatch, unfortunately. I assume a lot of these investments are actually coming from also from government. So obviously, I really like that you highlighted that fact. Leaving investment aside, I think there's a lot going on in the aluminium sector. And I think as Andy mentioned, definitely in recycling, and also as you mentioned, this is one of the parts that we can look at decarbonization. So increasing the circularity will be key. We see we are tracking ourselves the projects that are looking at decarbonization of the aluminum sector, and we see really there is a lot of movement going on. 16 projects we found in 2020, 50 in 2022, and now we are up to 90 projects. And they are also focusing on direct emissions. So 1/3 of these investments are in direct emissions reduction. So hopefully you see that coming through in your next review. We also published our first year Aluminium Industry Initiative report, and there also we saw that 80% of our membership have long-term targets. Again, this is a lot based on your data and the work that you're doing. So again, that is really, really key for the aluminium sector, that you also continue that work. And also about 70% really already have short-term emission reduction targets. Again, I think that's important. You're showing 2035 as your next step. This is where you want to see some significant reductions coming up. So to sum it up, we will continue prioritizing climate change, but we also are looking at other sustainability factors, biodiversity, circularity, and waste, of course. And yeah, we hope to continue to cooperate the good initiatives that you're doing, and yeah, please do more on aluminium. I think the end of the report was more into steel, so we hope next time we see a bit more on the aluminium side. So thank you.
Thank you very much, Marlin, indeed. And thank you both to Andrew and Marlin, not just for the engagement in the context of this webinar today, but for the many years that we've worked with both of your institutions on, hearing from the industry, a balanced view from each of your industries filtered through your global associations to improve our kind of take on what's happening on the ground, the refinement of the modeling, and all of the kind of peer review comments that you've left on our reports. It must be in the thousands by now over the years. Thank you so much for all of that engagement. I'm going to now turn to the Q&A portion of the webinar. We've had a few questions coming in, and I have some on my screen now. The first one is on Europe. How does Europe, with its high energy costs, retain competitiveness while decarbonizing its heavy industries? I think, Leo, I'm going to put that one to you, as Leo led a lot of the work on the CBAM analysis and some of the work that was presented earlier. So over to you, Leo, on that one.
Yeah, thank you for the question. Very timely question, because it's true that high energy costs pose an important challenge to some of the major largest industrial producers, like as we see the European Union, and the global energy crisis posed by the Russian invasion of Ukraine directly disrupted European gas markets, impacting heavily the European industry. And we see today that, for instance, Germany energy-intensive industrial production is down 20% compared to pre-crisis level, and it has not yet recovered. And this question of competitiveness, it's also high on the agenda at the European level, and we can only echo the findings of Draghi's report on European competitiveness, for which we were, as the IEA, honored to feed in during the last year. And so we echo the findings that highlights that decarbonization and innovation are the keys for the prosperity of the European industry. And even if during this transition, there may be some challenging periods, but eventually the final destination could well be a much more competitive position for Europe. And as we saw in the presentation as well, Europe owns older assets in many industries compared to its competitors. This is a call for urgent need for investments. Draghi's report estimates the investment gap in 800 billion euros per year for the whole economy. And in the area of near zero emissions materials production, steel in particular, we already see some progress where Europe where most of these projects are in Europe, and also we see some policy support thanks to the innovation fund that supports the hybrid and Stegra projects in Sweden, or the Commission that has approved in the last few years 9 billion euros in state aid from member countries for the development of these near zero capable steel projects. But also European strong climate policies are very important for creating differentiated markets for these commodities, which at the beginning may present a cost premium. So the single market is itself an advantage. But it's also true that at the same time that For instance, like transporting clean electricity or hydrogen may be a bit more challenging or expensive than transporting fossil fuels. So the location is really key for the development of these projects. And it's true that some part of Europe may well not host the most favorable conditions for the development of these projects. So here is where the partnerships with other countries that Richard talked about before are really important, and partnership with countries with more favorable cost fundamentals, in particular for clean electricity potential, is very important. And partnership with this country, in particular for the most energy-intensive step of the production, for instance, iron in the iron and steel case, could at the same time be a win-win situation, preserving some jobs and also the industry for the less energy intensive step, the steel making, which is also connected to the long-standing customers such as the automotive industries or other downstream manufacturing industries in Europe. So retaining those jobs and those connections with the customers are really important through these partnerships. Yeah, thank you.
Thanks very much, Leo. We've got a second question here. You've talked a lot about the trajectory of technologies in the presentation, but what is the role of government policy in bringing about these trajectories that you've shown? Perhaps I could put that one to Richard as well.
Happy to. Thanks very much for the question. So we've done a lot of work on this topic at the IEA, slightly separately from what we've done in this webinar. And in fact, we've actually recently institutionalized part of this dialogue on industrial decarbonisation policy with our member countries. We have a working party on industrial decarbonisation where these member governments get together and discuss this policy really at a working level, trying to push it forward. So that's been a great initiative. So the technology trajectories that we outline in some of our more ambitious scenarios, they won't materialize without policy intervention and a strong role from those governments. We don't prescribe a single solution in this area. There's a whole range of policies that work with each government having its own context. Each country operates slightly differently and has its own regulatory framework within which it sits. And so the different solutions might be better placed in one country compared to another country. But there's sort of a few different categories of things that might be needed. So one is a push response. So how can you support these near zero emissions material production? This could be things like loan guarantees for these producing projects, or sort of innovation grants to try and bring forward these technologies a bit further. Then there's a pull side as well. How do you create a demand for these materials so that industry can then see that demand and react on its own, invest itself? There's lots of options here. You can do innovative green public procurement schemes. You can leverage that public infrastructure to try and purchase some of this near zero emission steel, aluminium, and the like. Or you can sort of use mandates as well, potentially, to showcase that the demand might be needed and that producers can anticipate that in advance as well. Behind both of those is a sort of level playing field type enabling framework group of policy mechanisms that are needed there. It includes international cooperation on standards and definitions. It includes infrastructure as well. So lots of the solutions rely on large-scale infrastructure, for example, carbon dioxide transport and storage, or hydrogen production and storage that might be needed. And so we really need to scale up these and support these appropriately too. Talking a little bit about those common definitions of near zero emissions production and materials, that really helps provide a common understanding and a framework for government policies to build on. And it helps if they're sort of globally consistent as well. And so we work quite closely on that, and we're sort of facilitating that through the working party that I mentioned, and the Climate Club as well is interested in taking that forward too. That's just a quick overview. We can speak for a long time on this. But I'll just point you towards achieving net zero heavy industries. It is a report that we wrote a couple of years ago as an input to Germany's G7 presidency in 2022, and we had a follow-up report with Japan as well. And I'll point you towards those as initial places to go and learn about this in more detail. Please get in touch if you're interested on this. We can happily discuss this much further.
Thanks very much, Richard. We've got a third question here about the availability of workers and skills and so on. So do you consider that access to skilled workers or skilled workforce as a constraint when assessing the opportunities for emerging and developing economies in your analysis?
Okay, I guess this one's for me. So first of all, if we discuss emerging markets, know that in the ETP report, we have a whole chapter dedicated only to them. So if you want, you can have a look. But if the vision of more than 100 pages to read is too much for you, no worry. We also have a webinar, the same format as this one, that was dedicated just a few days ago to emerging markets. And it's available either on our YouTube channel, maybe already available, or at least soon enough. So you can have a look at that. When we discussed the availability of a skilled workforce, it is true. It is part of the decision-making process before making investments. We need to consider if infrastructures are available, if resources are there, if there's a market for the demand, and of course, if labor is available. And so one of the findings during this report is that the skill level especially for clean technology manufacturing is a bit more on the higher side. So you need higher skills to build the batteries compared to steel making. But of course, it doesn't mean steel making needs no skill. It is a difficult job, and it's not something you can improvise like that. So an example that comes to mind is maybe in India, where the percentage of the population that followed formal vocational training is relatively low compared to the OECD average. But when you consider informal training, then this number is much higher. So it shows that maybe formation through communities or driven by companies can be a way to compensate some of this problem and bring the skills required to the workforce, which gives more opportunities to the population to get a better job and helps the country develop. So when it comes to our work in general, it is true that for this report, we use a lot of data coming from advanced economies like the US, the EU, but it means that we are also lacking data in certain countries, mainly in Africa. So for future reports, we are exploring ways to collaborate maybe a bit more with different organizations, institutions to get better data and be more precise on this for future work. So please follow up.
Thanks very much, Alexandre. Actually, related to the last part of your answer there, we've had another question here on the opportunities for India. So can you touch on the opportunity for India in the net zero emission scenario? I think we talk more here about the announced pledges scenario, but if I could put that one to Richard.
Yeah, sure. So firstly, India's domestic market will continue its sort of development and its massive growth. And that's something we preserve throughout the different scenarios. So whether it's a net zero emission scenario or whether it's a sort of stated policy scenario with less development of near zero emissions materials, the development goals remain the same, I suppose. So I've pulled out a couple of numbers here from the charts that we had in the report about the announced pledges scenarios. So it's a net zero emission scenario that I think for India gets to net zero emissions by 2070, I think is the current pledge for India. So in 2023, India produced about 140 million tons of steel, and by 2035, it'll almost double to 260 million tons in that announced pledges scenario. So there's a massive opportunity for growth. And similarly for aluminium, we see a growth from about 5.6 million tons, 5.7 million tons to 9.1 million tons. Ammonia growing hugely as well as agriculture pushes forward on the subcontinent. Switching towards near zero emissions productions and the opportunity in that sort of net zero emissions scenario for India, the switch would unlock sort of those larger markets which would begin to sort of preferentially demand near zero emissions materials with a green premium. And there's a massive opportunity in pulling on that green premium there. beginning to see this maybe slightly with some of the carbon border adjustment policy mechanisms in Europe, and that's being mooted elsewhere. So India has a lot to gain by sort of switching and pushing towards that net zero scenario, and pushing towards near zero emissions materials production as well. Any change is probably not great for the incumbent and better for those disruptors who are building new capacity. Legacy capacity is less useful if we're changing the production technology. One thing to mention is that India's Ministry of Steel is active in our Working Party on Industrial Decarbonisation and the discussions on steel emission standards. So they're really part of the conversation, and trying to bring them in there is really important. But the pipeline for near zero emissions projects in India is currently quite small. So they need to really scale that up and push forward there. Many steel makers with near zero emissions material production projects in Europe have strong links to India. And that could provide quite a significant opportunity for knowledge transfer for those projects and really kickstart and leapfrog in India. So,
great, thanks very much, Richard. We have another question here that is, how do near zero emission materials support global sustainability goals like SDG 12, which refers to responsible consumption and production? So, I mean, I can maybe take that one. So, I mean, in our analyses here of each of these industry sectors, not just aluminium and steel, which we focused on in the context of this presentation and ammonia, but across all of the industry sectors that we model bottom up in our industry modeling framework at the IEA within the context of end use modeling for all the publications that you are, some of you will be aware of, Energy Technology Perspectives, but also the World Energy Outlook and other long-term scenario projections. In the context of that modeling, we first start with demand. We look at demand across a whole series of end uses that are relevant to each material. So in steel and cement and aluminium, we would be looking at construction applications, at transport applications, at consumer products, packaging, etc. Looking at how those evolve in a kind of baseline scenario. We then look at a series of material efficiency strategies that really talks to this point on sustainable consumption and production. These are, generally speaking, technical measures, much more technical measures than behavioral changes, but where we model behavioral changes, we do take into account the knock-on impacts on materials. An example of the latter would be the reduced use of single-use plastics, for instance, reducing our contribution of actual fundamental demand in the petrochemical sector. But beyond those kind of behavioral changes, we also look at these technical measures that I referred to as material efficiency strategies. The increased utilization of scrap facilitated through improving yields in various processes and having greater yields of scrap, greater yields of products per unit of input material. These technical measures within the plant would be one category, but we also have several on the end use side to do with lightweighting, life extension of things like buildings and vehicles, more intensive use of those assets so that not as many need to be built to provide a given level of final service. And these are all material efficiency strategies, as we refer to them, that help reduce the demand for overall material while providing the same service to the end user, and therefore providing a kind of more sustainable profile of consumption going forward in our scenarios. This, as I think Andy and Marlin mentioned in the context of each of their industries, makes a big difference to the kind of overall ambition level on near zero emissions technology deployments. Because if you can first, much like energy efficiency, which we refer to as the first fuel at the IEA, if you can avoid the use of a given ton or kilo of material in the first place, without diminishing the service that the material provides, we can then reduce the burden on deploying these near zero emission technologies that we've talked about in the presentation at length. I'm going to leave it there. We're at 1 minute to the hour, so I'm just going to say a few words of closing. So thanks very much firstly to Alexandre, Leo and Richard for all their work, but also their presentation today and tackling all the tougher questions. Thank you very much to Andy and Marlin. As I said, not just for your participation today in the webinar, but for the many years of collaboration and engagement that we've enjoyed with your institutions. And lastly, thanks to all of those of you who are listening. We're very grateful for your engagement, both in this webinar, but also in the context of reviewing our publications, many of you coming to our events and engaging with us via email and social media. And we greatly appreciate it. And we look forward to continued engagement with you in the future. Thanks again, and have a good weekend when you get there, all of you. Thank you very much.